Hello everyone to the next session in Forecasting for Data Scientists, Series Session 2, Global Models and Machine Learning for Forecasting. So let's start with the global models. So first I want to say that the name global models was introduced by Januszowski et al. In 2020, and it's arguably really not a good name, but it's the name that we got for now. So okay, so the idea is traditionally we have one time series that we see as a data set, and then we build one model per time series. And then we have the problem that low sampling frequencies and non-stationarities like structural breaks make usually that we don't have enough data to fit very complex machine learning models. And the M3, M4 data sets, they are put together under this paradigm, very different series with very different frequencies from very different domains, and just kind of, randomly put together because the idea was, well, we built for one per time series anyway, our models, so let's have very independent, diverse, different time series in these data sets. But then from these local models, we have a paradigm shift to the global models, where now the idea is that a set of time series is a data set. For example, a set of series from retail, smart meters, etc. So we now build a model across the series, and this is known under the names global modeling, cross-learning, multitask learning. We also sometimes call it pooled regression, mostly if the model is linear. And the idea is that now we have enough data because we have more series, and machine learning methods are suddenly competitive now. So just think about it. Let's say in the local model context, we would typically fit a model with few parameters to a single series, less than 10 parameters. ETS often has, 5 parameters. Or an ARIMA that has maybe, an ARIMA of order 3. So you have 3 coefficients, well, for the AR part, and then let's say order 2 for the MA part. So you have another 2 coefficients. So it's quite small amounts of parameters. But now let's say you have 10,000 series and fit a model with 5 parameters per series. You still end up with, let's say, 50,000 parameters in total. So if you fit local models, even though each model has a small amount of parameters, overall you end up with a lot of parameters. And the idea is we want to replace this with, let's say, a global model with 5,000 parameters overall, right? So 5,000 parameters versus 5 is a lot per series, but versus the 50,000 that you get globally from the local models, it's actually not an order of 10 less. And another very important advantage is that the overall complexity of local models grows when the data set grows, right? For every new series, you need more parameters, whereas the complexity of a global model stays the same, right? You can say, I want 5,000 parameters, and now you put in 1,000 series more. Well, you still use the same model with the 5,000 parameters. So global models can afford to be more complex. And this complexity can be added, for example, through longer memory, which means we use longer input windows, more lags, through nonlinearity, nonlinear, non-parametric models. So that's every machine, you can, like now that's where the machine learning models come in, neural networks, gradient boosted trees, whatever your favorite model is here. Or we can do data partitioning, which is now, because I said global models is not a good name, because if you now partition the data and you build, you have 10,000 series, you somehow partition them. So let's say it's from a retailer. Now you partition them for the different departments. Now you build a model for each department. It's now obviously not global anymore in the sense that it's for everything, but it's still kind of global in the sense that for each department, you build only one model and not a model per series. One confusion that I very often see in this space, and that I definitely needs to be cleared up, is global models are not multivariate models. Okay, so the global models, they learn across a series, but they predict every series in isolation. So the input is one series at a time, but the parameters are shared across the series. And that means they can work on data sets where series have different lengths and are not aligned, like M3, M4 data sets. So if you think about M3 data set, I mean, there were many series, but some would start years after the others, and they would start at different times and at different times. Have very different lengths, some series have 5 data points, others have 120 data points. And that's all not a problem for global models. But the global models do not take into account interactions between series. And in fact, it turns out that these concepts between global local models and univariate multivariate models are actually orthogonal to each other. So that means methods can be local univariate, global univariate, local multivariate, or global multivariate. When I say local, I mean local univariate. When I say global, I mean global univariate. When I say multivariate, I usually mean local multivariate, and global multivariate. I'm not really talking about it here in this course. Okay, so let me show you quickly how that works. So let's say we have here, a bunch of time series. Okay, and so now the way it works with a global model is we have our kind of input window and the output window, and now we shift that through the series until the end, right, during training. So that's how we build our training set. So you may remember, so let's say this is our time series, and now basically input output window, and we shift that through the series, and in this way we build our training matrix, for example. And now in the global model we arrive at the end of the series while we go to the next series and start shifting again, and in that way we build our training data set so that we get, for each like time series 1, time series 2, and they are just, the matrices are just kind of concatenated, and that's then how we train. Okay, now multivariate. And now if you think about it, the movement overall that you get through your data looks like this. Okay. Now in the multivariate case, so let's say we have the same data set of our time series. In the multivariate case, your input window is kind of a window over everything, because you want to model interactions between the series. They all need to be aligned now, right? So in the global case, I mean, what happens if they're not aligned? What happens if one is longer than the other? It doesn't matter, because you're just concatenating. Whereas here, you want to say, in the multivariate case, you want to say, okay, well, this forecast for this series here, right, in the output window, this is influenced by this data point here and by this one here, right? So something like my pasta sales will be influenced by the sales of, my pasta sauce sales will be influenced by the pasta sales, and the brand of one milk will be influenced by the sales of the brand of another milk. If I put in a promotion for one brand, these sales will go up, but for the other brand they will go down. So you have kind of this window that spans over all your series together, and now this window just shifts forward like this until the end. And here you often have these problems that, well, this input, like let's say you have 20,000 series, and this input window is like huge, and now the question is, well, can we sparsify it? Can we leave out things and so on? That's usually the question in multivariate forecasting, right? How can we get it down to a dimension where we don't have to look at all the interactions, everything between everything? Okay. A little bit of history of global models. So they actually date back to the early 2000s. There is some work, for example, this Duncan et al. 2001, Pooled regression is actually a standard statistics technique. I mean, for example, there's this book, Gellman et al. 2007, that talks a lot about it. So it's actually a bit strange that it wasn't really used in forecasting. In forecasting, I would say, well, one work that I'm aware of is this pooled regression for forecasting paper by Trapero et al. 2015. Then 2016, obviously, we have Smul and Kuber, and then CIF competition, where Slavik Smul used the global model. 2017, Deep AR and some other works from Amazon, Wen et al., that's MQRNN paper. We had an early proposal, Bandara et al. In 2017, and then after 2018, it really kind of exploded. A lot of work, many proposals. A bit in parallel and not so much noticed by the scientific community were the Kaggle competitions. There's a very nice paper by these two people, Borgia and Meltgard, in 2020 that summarize everything. These are some relevant Kaggle competitions. Walmart store sales forecasting 2014. Then in 2015, another competition, and the Rossmann store sales 2015, which is a data set that we still heavily use. The Wikipedia web traffic forecasting competition, that is also a data set we still heavily use. Then the Corporación Favorita data set, and another Recruit restaurant visitor forecasting competition in 2018. And so all these competitions were won by global models, and the latter four by either gradient boosted trees or neural network models or ensembles of these two. And then in 2020, obviously, there came the M5 competition, also held on Kaggle this time. That it was really dominated by LightGBM. Also Deep AR and NBeats were successful. And actually, a team of my students won a Kaggle Gold. They made 17th place in the competition out of over 5,000 participants. And they used an ensemble of LightGBM and pooled linear regression. And one thing that is actually quite interesting to mention here is that had they not done all this ensembling, the LightGBM, had they used just only the pooled linear regression component of their method, they would have been 19th place. Okay, so just linear regression, 19th place in M5. Their approach used 400 lags, right? So because, it's daily data, you want to capture the yearly seasonality. So you use maybe, for example, 400 lags. And what that obviously brings you also is that because if it's a linear model, the only way you can really bring in complexity is with longer memory. So yeah, you want 400 parameters, you need to use 400 lags in a linear model, right? So this type of modeling really can work very well. Linear models, long history is to give them some more complexity and then just train over the whole series, over all your series. Okay, so what that means is that global models, they have shown success to a surprising, even unreasonable degree. And the idea at the beginning was that the series have to be in some way related, similar, so that we can learn something useful across them. But nobody in these early papers really knew what means related. It was never really defined, and so I mean, we say now related in terms of this similarity of the data generating process, right? So it's certainly not correlations between series, because for global models, they don't have to be aligned or anything. So yeah, it's similarities of their data generating process. That was the idea. And then came across this paper, 2020, Montero Manso and Hindman, which basically stated global models can produce the same forecast as local models without any assumptions about similarity. So instead of fitting one complex pattern across the series, a global model also works quite well if it has to fit many simple patterns that are different in the series. So the outcome of this paper was that the series don't have to be related at all for global models to work. And one thing that people often miss here, even still in the foundation models, that's a big problem, and we'll get to that later, but the thing is that the series are actually related through the evaluation regime, right? So we evaluate as an average error across all of these series. That's what makes them related, right? So why can I train across all of the M4 data and it works well, even though these series have nothing to do with each other? Well, because in the end, how you're going to evaluate is going to be an average error, average SMAP, average maze of all the series. So you need to trade off between the series. Like if you get way worse in one series, but a little bit better in many series, that can make your average better, right? So that's important. The series are related through the way you are going to evaluate your forecast. Okay, so then there was a contribution from us, from my group, from a PhD student of mine, Hansika Heber-Malage, where we did a simulation study around when global models actually work well. Because you see that work by Montero, Manso, and Hindman, it's non-constructive. So it doesn't tell you how you should build such a global model that works well. It just tells you that there is such a global model. Yeah, and so what we did here was we said, okay, let's simulate some simple and some complex data generating processes, long and short series, homogeneous and heterogeneous data sets. So like we mix the DGPs wildly to get a heterogeneous data set, or we use only very kind of similar DGPs. You know, we use an AR3, and then we change the coefficients a little bit, things like that. Yeah, and so local linear models work well if patterns are simple and we have enough data per series. But like recurrent neural networks, like GBM, globally trained, that's competitive, both if they are simple but quite different patterns, as well as if there are complex nonlinear patterns. And the global models, they can improve the more series are available, whereas the local models can't. Right, so I think one outcome of this study was that, I mean, if there are very different patterns, it still depends, right? So if you have like in one series enough, in like if the patterns are very different, like you still need enough data to learn each pattern. So if across the series the patterns are similar, then that's fine. You just learn across, you can learn a pattern across series. If the patterns are different across the series, well, the global model will not do any magic, right? It will not be able to learn a pattern that is there only in a couple of data points in one series. But it can still learn this just as well as the local model could. And then, yeah, and then what then comes into play is this idea of averaging the way you evaluate as an average,